Good morning, everyone, and welcome back. So last time we were talking about the growth function and DC dimension, and now I want to continue and give discussion on general bounds. And after that, talk a bit about how we can do what we can do to instantiate this sort of analysis for neural networks, and maybe discuss a little bit of the geometry behind that. Right, so general upper bounds or general bounds. So as a reminder, what we were saying is that we formulated a notion of learning, of statistical learning, where we say we want to take this set of functions and from there, based on some data, be able to pick one candidate function that is going to do almost as good as you could possibly do within that class of functions, and with high probability, provided the sample is sufficiently large. And so now we formulated a particular option for doing that. That was the idea of minimizing the sample error, and with the hope that by minimizing the sample error, we would actually minimize the actual error. And as it turns out, we observed that if our class of functions was finite, then this worked out nicely. We used Hertz inequality and a union bound to establish the property that minimizing the sample error was a good idea. And then the discussion of the DC dimension was towards trying to establish a similar result for the case of a hypothesis class, which has infinitely many functions. And this is the result for a hypothesis. Excuse me, for a class of functions that contains infinitely many functions but has a finite DC dimension. We can use the sample error minimization algorithm, and that turns out to be a valid learning algorithm in the sense of our definition. So if H is a set of functions from some input space 2, 0, 1, or binary classifiers, and it has a DC dimension equal to D, and we pick L to be the sample error minimization algorithm, meaning that so the output that we produce, the candidate function that we pick, provided the sample C is the one that attains the smallest possible sample error for that sample C. Then L is a learning algorithm. Concretely, we can say that if we have M, the number of samples larger than D1/2, then the following is valid. So maybe we can look here at the second line. So remember that what we wanted is to establish an upper bound for the amount of data that was sufficient for us to have the good properties. And here this is the upper bound. So ML is the sample complexity for the learning algorithm. Here the sample minimization algorithm is bounded from above by this quantity. And maybe the constants here are not super important, but just that we discussed with 1/epsilon² times D, where D is this DC dimension. And right, so the point is, this is a number that we can find for integers of epsilon and delta. Epsilon is kind of the slack that we have, how far away are we from optimum, and delta is the slack that we have in the probability with respect to the sample of attaining that. Right? So, and the fact that this bound exists tells us that the sample error minimization procedure is in fact a learning algorithm for the hypothesis classes that have a finite DC dimension, because we can instantiate this bound. Questions? Okay. This particular statement that I put in here can be improved a little bit. So one can remove some of the factors that appear in here. So in particular, this guy here is log 1/epsilon. One can remove that. And now I want to continue and discuss how this upper bound is sort of optimum. So because what we're saying here is that if you have that many data, you can ensure that you're going to be able to pick the hypothesis that is close to optimal, but is that also necessary? So is there a lower bound for the amount of data that you need to be able to do that? And as a matter of fact, yes, that is, and I will show you that in a moment. Maybe before that, just what is kind of the key technical step towards proving that result is this uniform convergence. As I was saying, using the sample error minimization is motivated by the idea that the sample errors are tracking the true errors. And recall, we need to do that for all the hypotheses in our class, because we're not just trying to estimate the error for one function, but for all the functions in the hypothesis class simultaneously. And that's why we need to talk about uniform convergence. Uniform for the hypothesis class. And so that's the crucial step to obtain the learnability result from the previous slide. Is this statement is the uniform convergence of sample errors. It goes like this. We have H being a set of functions, and we have P, our Pauli distribution for input and output pairs. And then if we have an epsilon and M, we can obtain this type of bound. What is saying? We look at the discrepancy between the actual error of a function and the empirical error, so the sample error of that function. And we want to consider the bad event that this discrepancy is bigger than epsilon. Epsilon is our, let's say, desired accuracy. And we're going to consider all those events, so for all possible functions in our class. So, if any one of those functions breaks the bound epsilon, then we're saying that a bad event happens, and the probability of that being the case is going to be bounded from above by something that looks pretty much like the Hertzing inequality. And we have here a factor at the front that looks pretty much like the union bound that we had before, but now instead of taking the union bound for the cardinality of the hypothesis class, we're substituting that essentially by the DC dimension of the hypothesis class. There are a couple of things that are a little bit different here. Instead of having the, not the DC dimension, excuse me, the growth function. The growth function, we're evaluating the growth function at 2m rather than m, where m is the size of the sample, and we have this prefactor of 4 in there. So it's a couple little changes that happen in there. But otherwise, in the large scheme of things, this looks like the Hertzing inequality plus the union bound that we have. So in a way, we have reduced the problem of learning with the hypothesis class that may have infinity in the hypothesis to something that looks like learning with a finite hypothesis class. Okay, so this is one of the central results in learning theory, and so I didn't want to show you the result. As for the proof for this works based on trying to compare the error. So this discrepancy between the error of hypothesis and the sample error. Compare that and bound that by the error between two sample errors and two different samples. So we consider two different samples, we compare how different they are from each other, and we use that to upper bound the probability of the discrepancy between the actual expectation and the sample mean. And from there is that we end up getting this factor of 2 here. Then there is, additional steps. There is, it's kind of a nice proof, but maybe a little bit too much detail to include here. Then I was talking about the lower bounds. So the fact that is it necessary to have that many data in order to obtain these guarantees? And yes, indeed, one can obtain a lower necessary bound that tells us basically what is the complexity of learning, how much data do you have to have observed in order to be able to pick a hypothesis that is good. It goes like this. So we have the hypothesis functions, H, and let's say that they have a finite DC dimension D. And then for any learning algorithm, so whatever method that we consider that maps data to candidate hypothesis, the sample complexity, recall we have defined this as being the minimum number of data points that we need to satisfy this epsilon delta condition is at least this big. So it's like 1 over epsilon squared times d. And this is more or less the same behavior that we have for the upper bound. All right, and so there are a couple other kind of cases and modifications that one can instantiate in here, but maybe let's just think about the d divided by epsilon squared. So that's indeed necessary. We cannot hope to learn with fewer data, at least not in this sense. I think it's a question that had come up at the very beginning, like, can we do with fewer data? The machines need more data than we do. And so this is going to say, you cannot, whether you're a human or a computer, because if you have fewer data than this, you will not be able to satisfy this requirement. Now, of course, if you wanted to learn with fewer data, then you would need to modify the definition of learning that we're considering. You would say, I don't want this to be valid for every probability distribution, or you're going to say, I don't want this to be for a particular epsilon, or only for a certain range of epsilons, or something like that. And then you might be able to do that. Or you could say, maybe my samples are not independent, and you're going to actively go and choose them in some particular way. And all those are modifications of the settings that might allow you to break this lower bound.
Is it two-dimensional and solid for 0, 1, or you can extend it to?
Okay, this result is stated for binary classification, but there are analogous results for other cases as well. So if it is non-binary, or also if it is continuous. Conceptually, this is maybe the most classic case, and most illuminating maybe. But
so you can also look for continuous.
That's right. So then in those cases, one will define a different notion of complexity. So instead of talking of the dimension, which recall this dimension is defined based on the number of dichotomies that you can represent. So you will need to identify a different complexity measure. And there are definitions that are tailored for problems where you are doing regression or continuous value predictions.
Right. Is there always some kind of canonical choice for a hypothesis given any data?
That's an excellent question. I don't think so. Yes and no, because let's say that you actually knew the answer to a problem, and you could say, I'm going to pick my solution to be the hypothesis class. So that's not very helpful. What is helpful is if one can identify some sufficiently general priors or properties, but that don't require too much work. And this is in fact what has been the motivation for, let's say, deep learning. You say, I'm going to want to use as a hypothesis class a deep neural network. The idea being that this is incorporating some aspects that we think happen in real life problems. So like the computation that you need to do to find a solution, it may be sequential, you have multiple layers, or has a hierarchical structure that can be captured well by the compositions or compositional structure in the network. And so this is a prior. This is just a guess. And then you may try to use that for all problems where you presume that this is natural or helpful. And whether that's true or not, that's something that one can, of course, then investigate empirically and theoretically. In some cases, I suppose that you can come up with more and more refined priors. And so model selection is in itself an interesting and important problem. There's another whole track, let's say, of statistical learning theory that deals with model selection and how you can, for example, start with a smaller hypothesis class if you only have so much data. But as you imagine that you can collect more data, you allow yourself to pick a bigger hypothesis class. Because what we're seeing here is that if the complexity increases, you need more data. And conversely, you have more data, maybe you can pick a bigger hypothesis class that allows you to do better. Part of the reason for this is because recall that this notion of learning that we're discussing, where what we want to accomplish here is that the error of the hypothesis that we end up taking at the end is close to the best possible error within our hypothesis class. But that best possible error within our hypothesis class could still be bad. So it could still be that we're doing many mistakes. And so, by picking a bigger class, you may be able to drive that down, but then you're going to need more data. And so, how to pick one based on the other, there are ways to study that. Structural risk minimization is one investigation for that. Other thoughts? Okay, then. So these two things together essentially lead us to this sort of statement here that the distribution quantifies the sample complexity for learning binary classification problems. And we have an upper and a lower bound. So let's say MH, this is really the amount of data we need to get this epsilon delta learning. And if we have a hypothesis class of finite DC dimension D, then these things bounded above and below by essentially the same quantities. So it's 1 over epsilon squared times D plus log 1 over delta and some constants. Right? So asymptotically this is tight. So not much we could do there. Next, sort of a summary in here is just to tell you, there are multiple equivalent ways of formulating this, or there's multiple things that are equivalent. First is to say we selected a hypothesis class, let's say a neural network, and this is learnable. This is equivalent to stating that the dimension of the hypothesis class is finite. Is equivalent to stating that the sample complexity for the hypothesis class for epsilon delta learning is like this quantity, 1 over epsilon squared log 1 over delta. Or equivalently, that is slack, so that the gap that we have from the best possible hypothesis behaves like this, like square root 1 over m log 1 over delta. This also is equivalent to saying that the growth function, so how big an input data set can you shatter, how big a data set can you, how many dichotomies can be represented over a finite data set of finality m, that this is bounded by a polynomial. And remember that, so when the DC dimension is finite, what we observe is that the number of dichotomies that you can represent over n data points will be controlled like that. So we can only continue going polynomially after passing the DC dimension. And also, we could also talk about this sort of uniform convergence. So results. So if we can show uniform convergence, then we can also have these statements. So that we are able to track the actual error for every hypothesis in our class uniformly within the class. So some bad event happens for any of the hypotheses, and that is at most uniformity delta. And this is true for any data distribution.
So does it mean that if your hypothesis is not learnable, then your growth function will exponential?
That's right. That's right. So remember, because in this uniform convergence result that we have basically the growth function multiplied with this exponential term that became exponential. But if the growth function is exponential in itself, this whole thing might be just constant. And so if we cannot ensure that the quality of the bad event is going to decrease arbitrarily low, no matter how big we use the data. All right. So for this, I have based this on some of the notes of Abu Mustafa, people learning from data, and some of the people, Anthony and Bartlett. A couple of people asked me. So here are the references. I put some background material in the appendix. So now I'm going to switch slides, and So give me just a second.